I'm Ritika Ramesh. Like Laura said, I'm presenting my paper on the system VPNalyzer. It's a little bit of a tongue twister, but it's just VPNalyzer. And I developed this with my colleagues at the University of Michigan to investigate the VPN ecosystem. Over the past decade, the fame and demand for commercial VPNs has been steadily increasing. What was once developed as an enterprise security tool has now found its way into a regular internet user's toolbox. Now, this could be in part due to the numerous reports of censorship, ISPs selling user data, and in the increasing prevalence of surveillance, all of which have led to an increased public awareness of online risks and access restrictions and so on. Now, we noticed that VPNs are increasingly being marketed seemingly as a solution to these problems. Users have started adopting VPNs to protect themselves from surveillance, to access censored materials, to access work and university resources, especially during COVID lockdowns, among many other reasons. And all of this has fueled the VPN ecosystem to grow into a multi-billion-dollar industry. And this industry, unfortunately, has a bad reputation. But that's understandable considering the number of news reports and stories that have highlighted the deceptive behavior of some VPN providers. But with that said, it has received relatively little academic attention, with the last reliable investigation being done over 4 years ago. And the problem is that these previous reports and studies have all been lab-based and have used inconsistent heuristics amongst themselves, which prevent the monitoring of important issues over time. This is also in part due to the large amount of manual work that's usually involved in studying VPNs, and further, these studies were limited in the scale and the types of VPNs studied as well. This is also, again, going back to the large amount of manual work that's needed to even set up such tests. So considering all of these challenges, it was clear to us that bringing transparency and better security to consumer VPNs requires a completely different approach. So with that in mind, we built VPNalyzer as a system to address all of these challenges in studying the VPN ecosystem. First, we wanted to create a robust test suite that can test important features of VPNs, and we wanted this test suite to be extensible as well. So in short, we just don't want another evaluation done by researchers like 4 years down the road to start from scratch. Next, we also wanted to facilitate the ease of testing for both users and researchers. So we wanted to help researchers move from a lab-based manual testing environment to real-world measurement. And on the user side, since they have very varied threat models and different use cases for VPNs, it's natural that different types of users will prefer different VPN products. And with the hundreds and thousands of products on the market, we have to start leveraging users via crowdsourcing to be studying this at scale. First, before I go into the bulk of the talk, I'll go over a high-level view of our system's design. A user will be able to download the tool from our website and run the measurements at the click of a button, which runs our test suite containing 15 measurements for both the VPN and the ISP links. And once that is done, we get consent from the user to upload the results, which are then analyzed and displayed back to them using a uniquely generated link. So today, I'll talk a little bit about the journey to getting here. This is a lot of things from here I was not able to include in the paper because, again, this is all experimentation and like trial and error kind of things, which basically ended up being the actual measurements that we currently run. So there are plenty of design challenges that were like based on our end goals and experimentation that we had to do. The first of which was deciding on what exactly we are going to implement. We had the idea that we wanted to automate most of the testing. That was one of the biggest challenges that I mentioned. In a way that's easy for both users and also researchers to kind of run periodically if they want to monitor important issues over time. So we explored the different trade-offs, right? We initially explored creating a browser-based test suite or a website-based test suite or a browser extension or plugin. But none of these alternatives could provide the level of functionality and the fine-grained access that a convenience of a desktop tool offers us. For instance, web-based tests are restricted in the types of requests they make, and browser extensions, while they're easy for users to adopt and are definitely cross-platform, they also have limited functionality when it comes to testing features like data protection during tunnel failure. But this is not to say that these other two types of measurements cannot collect meaningful data. For instance, from the web-based tests, we can run bandwidth measurements, we can run static IP to geolocation lookups, we can test for certain kinds of DNS leaks, and there are different websites that do that for various different reasons, and not typically for VPN users. And from the browser extension, you can run measurements in the background, which is going to be useful in the long run, and also test for things like DNS leaks and tracking capabilities when the VPN is turned on, and so on. But a native desktop application affords us all of the above basically, and a lot more capabilities while also being easy for a user to download and run, and easy for researchers as well. So once we had selected the desktop application route, we used the open source Electron framework, which we chose for its cross-platform compatibility and native API availability. We developed the UI for the app using React and implemented the measurement code using Node.js. So one full experiment at the moment runs on average for about 20 minutes. Again, this varies based on the operating system, the tool that you're downloading, but it's generally around 20 to 25 minutes. And the tool right now contains 15 tests or measurements, which we divide into 3 main umbrellas. This slide just contains a flavor of the tests that we run. We test for various aspects of service, misconfigurations and leakages, and certain security and privacy essentials. So the second item I'll be focusing on is the need for a sustainable cross-platform solution. The insight behind this design need was that for something to be a systematic investigation of something, that's in this case desktop VPNs, it's necessary that the investigation covers all the different ways that the service is being offered. So a systematic study of VPN applications demands a cross-platform solution for an investigation like this. The closest prior work done in 2018 only studied macOS applications and also kind of focused on OpenVPN configuration files and so on. But that isn't sufficient to get the whole picture. Because as you all know, not all OSs are made the same. And for instance, different VPN providers may offer different sets of features or implement features completely differently on different platforms. So let's take an example of one of the tests that I'm going to be using for the rest of the talk, the protection of user data during tunnel failure, which is a key privacy feature. The implementation of such a feature varies from one VPN provider to another. It could be in the form of firewall rules. It could be something that kicks in when the tunnel drops, like a kill switch. And naturally, the way that this is implemented across different operating systems will be different. So I'll first explain how we implement a test for this, and later in the talk explain how we enhance that measurement or how we got to that point. If you attended my talk yesterday, you would have heard me explain this particular test, but let me go over it again really quickly. So let's think about how you would detect traffic leaks that occur during a sudden tunnel failure. Conceptually, how you would do this is to create an allow list of specific hosts that are needed for the test, and block all traffic except to and from hosts on the allow list. So once you do that, this basically causes a tunnel failure because your machine wouldn't be able to connect to the VPN server. Now, if the VPN's leak protection is effective, the traffic to the hosts on the allow list should also be blocked. While this seems sort of straightforward, it demands complex platform-specific implementation because, like I said, it's implemented differently on different OSs, and there are different lower-level things that we need to take care of. So we do that in 3 stages. The first of which is bootstrap phase, which takes place when the user clicks the button to start tests, basically. And in this phase, we request administrative privileges. We lock the firewall state and initiate sessions that need to start in the ISP phase. We then ask the user to turn on the VPN, and the test suite begins to run. For this particular test, it first has an initialization phase where we set up necessary components for the test, which is again platform specific. So on Linux, that would look like adding new chains on the IP tables. And on Windows, we log the PowerShell and the net security versions. And on macOS, we check if the PF or packet filter allows us to add custom anchors. And we then enable the PF and obtain a token that's needed to reverse this. We then log the firewall state before we make any changes to it. Next, we create an allow list that I mentioned before and add the hosts that we need for the detection of the leaks alone. For now, I'll just focus on the RipeStar data API endpoint. I'll get to the other ones a little bit later in the talk. To the RipeStar data API endpoint, we're going to be sending a what's my IP data call to basically confirm if the traffic is still going through the ISP link or not. So once we create the allow list by resolving all of these domains, we modify the firewall, apply our custom rules to induce tunnel failure, and make sure we don't reset any existing rules, and log the state of the firewall again. So once our rules are applied, like I said, it will block all traffic to any port to and from all hosts that are not on the allow list. This means that there can be no communication to and from the VPN server. So we can now move on to the detection phase. We conduct the detection phase for about 120 seconds, which ensures that there is more than enough time for the VPN application to diagnose and act upon the tunnel failure. So moving on to the detection logic. To detect any possible leaks, we periodically query the RipeStar data API with the what's my IP data call on both IPv4 and IPv6. So if some data leak protection exists, the queries will time out. But if there is no data leak protection from the VPN provider or it's a badly implemented one, the query will go through the ISP and reach the endpoint, and it'll return the user's ISP IP, which is the case that's depicted in the figure here. Now, with this measurement, we cannot confirm if the VPN's leak protection mechanism is completely effective or bulletproof, but rather we look for leaks in the implementation, and we look to measure failure to protect traffic during tunnel failure. And we take another step to validate our result for this particular test in case the VPN connection is governed by a stateful firewall. So finally, again, once the tests are done using the VPN connection, we ask the user to turn off the VPN and we run the test suite again. For this particular test, we just log the firewall because you don't need to run all of the tests for the ISP connection. And this is the generalized workflow for an experiment. One thing I want to highlight here is that when we request administrative privileges, if the user denies it, we still continue with all of the tests that don't need this administrative privileges. So basically, the choice of conducting an advanced set of tests lies with the user. So, and again, new tests can be added to the test suite as long as they can function in these three phases. Yeah, so we conduct this process in these three stages and run the same test from the VPN and the ISP case because it's necessary to do so to confirm and corroborate our observations. And the ordering of the tests is also important. That is, VPN tests happening before the ISP test is also important. And the reason why is something that ties into our next item. The third challenge was to ensure that the measurements themselves are conducive to tests from both the VPN and the ISP case. So like I said, the test suite is going to run the relevant measurements for the VPN and the ISP one after the other. And we want to be able to corroborate and verify results using the ISP results as well. So for instance, when we decided on adding the bandwidth and latency test to our tool, this is where the ordering of does the VPN go first or the ISP go first matters. The idea was to have a way to calculate the overhead that a user would incur by using the VPN. So in other words, calculate the performance penalty that they may have to pay or the enhancement that they may receive by using the VPN in terms of bandwidth and latency. So to measure this, we need to measure the bandwidth on both the VPN and the ISP links. And we decided on conducting this measurement using measurement lab servers or MLab servers. So how you would go about this is to find an MLab server and use it to run several NDT7 measurements on IPv4 and IPv6. Now, the nuance about the validation of this test is that if we find an MLab server in the bootstrap via the ISP phase, we will find one that's closest to the user's real location, because that's how the server finding algorithm works. It will find one closest to the user's real location. But when we measure the bandwidth and latency through the VPN server, it may cause a bloat in the measured performance overhead. So that's due to something called the trombone effect, which is what's shown in the figure here. And that's because of the added time it takes to travel to the VPN and back to the server, especially if the VPN is farther away from the user. And like I said, the server would be close to the user. So to allow a fair comparison of the quality of service, we have to find an MLab server closest to the VPN endpoint and run the NDT7 or network diagnostic tool measurements to basically estimate the bandwidth and latency on IPv4 and IPv6. And we also use the ISP and VPN results in other measurements, for instance, to verify that the DNS servers available in both cases, are they the same or are they different? And to basically to confirm IP leaks and data leaks to ensure that the traffic is actually leaking to the ISP and not just coming out of a different VPN server, for example. And for TLS fingerprinting, we also run the TLS fingerprinting test from both the ISP and the VPN to test whether there's a TLS terminating endpoint on the path when you're connected to your VPN. Now, the next big portion of this talk, I'll focus on how we validated our tests and the process of how we discovered issues with previous work and tried to improve upon them. So we extensively researched all the prior work and methods that researchers have used to study VPNs and also to study networks in general under various different contexts. So we cover essential tests from previous work with about 6 measurements, I think, that take direct inspiration from, that we take inspiration from, and 9 new measurements that we implement with our own methods. Before I move on, I just want to talk about the geolocation test here. So that's one thing that, based on the time that it's taken, that has passed from that measurement to now. One thing they do with that test is that they use RIPE atlas anchors to conduct kind of like a constraint-based geolocation measurement. And at the time that they did this study, there were only 250 RIPE atlas anchors that were stable enough to conduct this measurement. But now, when we thought about implementing this for VPNs, we found that the number of RIPE atlas anchors has expanded to about 750. So we are able to kind of conduct way more measurements using the RIPE atlas anchors and do this constraint-based geolocation algorithm in a much more efficient way than the situation was when they did it. The next thing I want to focus on is measuring, again, data leaks to internal failure. We looked at how other studies have done this before. And while I explained a little bit about how we conduct the measurement, I wanted to talk about the experimentation that we did to actually get to that part to basically end up with the test that we end up doing. So again, like I mentioned before, conceptually studying data leaks to internal failure is straightforward. Induce a tunnel failure and observe if targeted queries are succeeding and going through the ISP. But this may be a clean and easy thing to do in a lab-based testing environment. It's going to be much easier to see this in a lab-based testing environment, like the ones used in previous studies, where between testing 2 different VPN providers, they basically reset the entire macOS VM to ensure isolation. But the real world is much more messy and much more complicated. And since we want researchers and users to use this tool in a much more realistic setting, for example, on a personal computer, the first thing we want to consider is that our tool must not tamper with the user's custom firewall rules. And second, at all costs, we want to avoid hindering the VPN provider's leak protection mechanism when conducting our measurements. Because if we interfere with the protection mechanism, we could potentially end up with false positives, which is not going to be good for reporting. So this is one of the major drawbacks that we found in the prior work that I mentioned. They basically did the latter while conducting the measurements. So according to the code on their GitHub, our understanding is that the implementation modifies and enables the packet filter using the pf.conf file, which when you do that, you would flush any dynamic anchors that the VPN has inserted by not using the pfconf. And one thing we wanted to do is ensure that we don't make the same mistake. And I'll explain a few of our learnings from designing this experiment about how we avoid these pitfalls. But before that, let me give you some background on what I'm talking about. The prior work from IMC 2018 by Khan et al. Tested VPNs on macOS. So for the purpose of this talk, I'll just stick to the macOS implementation of this test. So we use the PF, the packet filter program, which is the main piece of software that is part of OS X for firewalling. We make use of anchors, which are some things that you can hook onto the PF, and they're just a collection of rules and tables that you can group under a specific anchor name. So it makes it easier to engage and disengage them. Now, the ordering of the anchors on the firewall is important because when the PF, when it comes across an anchor rule contained within the main rule set, it'll evaluate the rules contained within the anchor before going back to the main rule set. And PF using PFCTL also provides a way to enable and disable PF using a reference token. So we leave it in the state that we found it, and PF is only disabled after the last reference token has been disabled. Next, while experimenting with how we want to implement this test, we tried putting our anchor right at the bottom of the rule set. But again, that was obvious that it became useless because any prior rules that have the keyword quick would make our tunnel failure void. Because what the quick keyword does is that if the packet matches that particular rule, do not check any further. So this will result in us not inducing the firewall, like the tunnel failure at all, if any prior rule had the word quick. A keyword. So what we wanted to do was to insert our anchor as close to the top as possible. This is apart from system anchors and so on. So we did that, and when we tested a bunch of VPN providers with our new implementation, we saw that once tunnel failure occurs due to our custom rules, some VPNs try to fix this issue by simply just resetting the firewall on the user's machine and pushing their anchor to the top, which what happens is that it basically clears our rules and removes the tunnel failure. But in this case, our results, yes, would say that we found no leak, but that it's actually just that the VPN simply overrode our rules, and it doesn't indicate whether the VPN's firewall rules themselves have any issues. So first, we opted to be conservative in our measurement and report no leaks in this case. But something about that intrigued us and kept poking at us. We wanted to see if we can actually look into the rules that the VPN providers apply on the firewall to supposedly protect the users against tunnel failure, but see if they're actually secure. If we can find any loopholes in the VPN firewall rules to see if we can exploit it in our testing. So naturally, we ran some experiments and captured them and parsed these rules. And from this exercise, we found that VPNs allow list certain queries to certain IPs themselves, which is probably to the VPN servers, and sometimes they allow list queries to any IP, but from like particular ports. So among those, what we noticed was that some VPNs allow list DNS queries specifically. So what we did was to design a measurement to see if VPNs allow any and all DNS queries to leak during tunnel failure. And of course, we found that, we found these rules in a couple of VPNs that we tested, but our theory, our hypothesis was that since VPNs do this to facilitate reconnection during tunnel failure, it's definitely worth testing in a much more broader context. So, and I also want to note that in our threat model of a network provider or an ISP targeting a particular user, any attempt at reconnection will just not work because the ISP or the network provider is going to drop all the traffic that it hasn't allow listed. So all these attempts at reconnection will still fail, and in the meantime, the ISP would still observe all the user's DNS queries. So we wanted to think about how we would test this. So naturally, we allow list all the IPv4 and IPv6 IPs of authoritative name servers and recursive resolvers belonging to popular public DNS services, such as Cloudflare, Google, OpenDNS, and so on. And after inducing the tunnel failure, we periodically make DNS queries over TCP and UDP for every 100 milliseconds. An example of the kind of query that we make is shown here on the right. And for the responses, I've basically shown a template of what, where the response would be and how we would extract that IP to see if the query has indeed leaked to the ISP. But this was, not that wasn't enough. So we also, verified that the queries have leaked by looking at the packet captures on the ISP interface. So the example answer here from OpenDNS public, the DNS server contained the public IP of the user's ISP, which made the request. So this is how we would extract the response in the end. So in summary, by looking into and conducting multiple different rounds of experiments with different VPN providers, I was able to gather a few of their behaviors. Like I've told you before, the ordering of the anchors in the main rule set is important, and it's important that our anchor should be at the top because it's going to be basically a catch-all and block all the connections and only allow certain ones, which we hope the VPN provider is going to catch and disallow. And next, like I mentioned, some VPNs simply reset the whole firewall when they detect a tunnel failure. So we should be able to carefully coexist with these type of VPNs and not break the user's, firewall rules. And that means we will be conservative in our results. And finally, we found that some VPNs deliberately allow certain types of traffic in their firewalls, and we found ways to kind of test that and report on how many VPNs just simply allow DNS queries to go through. So by focusing my talk on just these 4 design considerations, I just wanted to capture the kind of experimentation that we did when we designed the VPNalyzer system. Once developing the tool with the 15 measurements that I mentioned, we put VPNalyzer in practice to evaluate the current state of the VPN ecosystem. To that end, we tested about 80 popular VPN providers ourselves and found several previously unreported issues. And I'll give you an overview of just the biggest issue we found, which is, no surprise there, it's traffic leakages. We found that not only is IPv6 support by VPNs pretty low, 5 VPNs even leak IPv6 traffic to the user's ISP by simply just allowing it to go through. Even our university VPN was one of them, and we immediately reported this to them, and we saw that it was fixed. Their excuse was that they don't support IPv6, but blocking it is the least that we can do. And alarmingly, when we saw that when we were measuring traffic leaks during tunnel failure with just the default configurations of VPNs, we found that 26 VPN providers, which is 1 in 3 of the VPNs that we tested, leak traffic to the user's ISP upon tunnel failure in their out-of-the-box configuration. And when we went, this is, I just wanted to mention that 18 of them leak all traffic and 8 of them simply leak DNS traffic, like I said, in an attempt to facilitate reconnection, but it still leads to user queries during that time being leaked to the ISP. We also went a step further and tested some VPN providers in a custom, more secure setting. That is by turning on relevant security and privacy settings available on the VPN application. And we still found that 10 VPNs leak traffic upon tunnel failure. And even though the features call different things on different VPN providers, we saw that 6 out of the 10 here had the recognizable kill switch feature enabled. And we also filed responsible disclosures regarding our findings based on all of the traffic leakages that we found to the relevant VPN providers. And we also found that 2 VPN providers only acted on browser traffic. This is without informing the user, and both of these applications weren't browser extensions or anything. They were actual VPN applications that you have to download, but they still only tunnel browser traffic by default. Yeah, so again, this is just a summary of all of the results. I just wanted to highlight that it was 33%, which is 1 in 3 of the VPN providers that we tested had tunnel failure in their data leak during tunnel failure in their default configurations. So some good news, just to give you some, is that our disclosure and communications with VPN providers have led to positive changes in at least 4 VPN products. And apart from these findings, we took several efforts towards our ultimate goal of making the VPN investigation easier and helping users make informed choices. So we worked with Consumer Reports Digital Lab, and they independently deployed the VPNalyzer tool as the first in a line of a series of investigations to provide recommendations to their users. And this also served as the first real-world evaluation of our tool. And we are launching the beta version of our tool during NDSS here, so you should be able to download it and test it out, and we'd love it if you can give us some feedback. Our ideas for the future are basically focused on our ultimate goal of improving the VPN ecosystem by leveraging crowdsourcing. But in this paper, our findings already shed light on the lack of standardization and the lack of regulation by highlighting that various features are simply just turned off by default, and the non-standard jargon that VPN providers use to refer to these features make it much more difficult for users to find and turn them on or utilize them. Finally, we hope that VPNalyzer benefits researchers like us and users also, and that the disclosures that we filed ultimately help make the VPN ecosystem more secure. So with that, I'd like to open the floor for questions.